Log on, tune in, find out. Another good idea from Cambridge.
Words, yeah. Well, it's a pleasure for me to welcome you to the third and final workshop, which is taking place in the framework of the program on kinetic equations. Yeah, actually, David said it all. I think I don't need to say much at this point, except that we will have a conference dinner for which you should sign up if you haven't. If I'm not mistaken, it's going to take place in Emmanuel College, which is really a very nice location. And that's going to be Thursday, if I'm not mistaken. Okay, so as far as the organization goes, I think we are there, and then we can just go to science and start with the first speaker. Shi Jin, our co-organizer and friend, and she doesn't really need an introduction, except maybe I should say that he's the chair at the University of Wisconsin, at the math department of the University of Wisconsin-Madison, which is one of the few places which is still colder than Cambridge at this moment. Yeah, so let me welcome Shi, and she is going to speak to us on Eulerian surface hopping for quantum dynamics.
Okay, so thanks Peter for a nice organization. Well, I'd like to take this opportunity to thank the Cambridge Newton Institute for allowing us to organize this program. And I've heard a lot of nice words from participants. So it's a really great place to be and to meet your colleagues and talk about mathematics. Well, thanks the local organizer Peter, who made all these events possible. All right, so because Claude Bardot, I'm organizer, I'm not supposed to give a talk, but since Claude is not here, I just stepped in to fill his void. So I'm going to talk about some recent work that I did with a couple of PhD students. Peng Qi, he's in medicine, and Jiwen Zhang is a PhD student in China's Tsinghua University. All right, so this is my mathematical interpretation of the difficulties when you want to do a simulation at the quantum level. So I kind of classify into two limiting problems. One I call it the large M problem, the other one is small h bar problem. Okay, so that kind of summarized all the main difficulties. We know that if you can simulate at the quantum level, then you'll basically solve all the problems. But however, it is very difficult for the following reasons. First is that usually you have to deal with n-body Schrödinger equation. Well, what comes out from this n is because you have to solve Schrödinger equation that's defining dimension 3n. To give you an idea how big the n is, for example, for CO2, it consists of 3 nuclei and 22 electrons. So 3n in that case is 75. So you have to solve a 75-dimensional Schrödinger equation. Okay. And for benzone, it has 12 nuclei and 42 electrons. So 3n is 162. So problem of this is that these are linear equations. Okay, so you can easily write any method, find different structure method, put in the computer, then the computer gets stuck. So that's the problem. So it's not an issue of how to discretize. It's the issue of how they put in the computer and compute. So there has been a lot of theories and methods developed to really address this issue. For example, you can use mixed quantum classical mechanics methods. I give you examples: Ehrenfest approach, Born-Oppenheimer approximation, and more recently, Carr perennial ab initio molecular dynamics, and so on. So these are the methods that kind of instead of solving quantum mechanics in the entire domain, you kind of solve it only locally and couple it with classical mechanics. And another mathematical tool that has been used to really reduce n is the mean field approximation. Well, for example, you instead of solving dimension 3m Schrödinger equation, you try to write as a dimension 3 Schrödinger equation. Okay, use one particle representation. So, for example, Hartree approximation, Hartree-Fock theory, and density function theory, and so on. So those are the so-called mean field theory. Well, even if you write it as a mean field approximation, it's equation 3D, there are still major difficulties. So that's the next difficulty, so-called small h bar problem. So we know that quantum mechanics lives on the scale of Armstrong, which is 10 to the minus 10 meter. Okay, so it's 0.1 nanometer. So it's very, the validity, the scale is very small. So typically it ranges from angstroms to hundreds of nanometers. So even if it's a three-dimensional problem, it's still very difficult because if you say you want to simulate the visible lights where the wavelength is in the order of hundreds of nanometers. So you want to simulate in, for example, the size of this room where the scale is in terms of meters, they're about 1 million to 10 million wavelengths. And we know for every wavelength you need a few more match points. So if you want to put this computation into your computer, it just your computer cannot store so much data. Okay. So in one dimension it's about 10 to the 6 to 10 to the 7. In 3D it's about 10 to the 18 to 10 to the 21. That number of points. So again, here the difficulty is we do not know how to write a numerical method for these equations, which there are a library of different methods. It's really that the computer is not big enough. Okay. So of course, these two limits are very different limits. By taking here, usually you can take n to infinite, and then you get some reduced equation. That's what the mean field theory is about. Here you can usually take small h bar, let h bar go to 0. You get some kind of a classical, semi-classical limit. So these are very different limiting process. But in the case of Oppenheimer approximation, actually these two limits are related. So that's what I'm going to talk about here. Because in the past I've been working on this small h bar problem for a number of years. Okay, so this is the embodied Schrödinger equation. So it takes this simple form. So phi here is the complex valued wave function, and depend on time t. So x is the position of the nuclei, and y is the position of the electrons. Okay. So x is in dimension r capital N, y is dimension r little n. And this h is the Hamiltonian, which consists of several parts. So this is the nuclear kinetic energy, and these are the rest of the Hamiltonian that has to do with the electrons. It has three parts: electronic kinetic energy. Then these are the interactions. Okay, these are interactions between electrons, interaction between the nuclei, and interaction between nuclei and electrons. And of course, again, the difficulty here is really this capital M plus little n. So that's the high dimensionality of the problem. So if you rescale the problem, so let's assume that these are the mass of the nuclei. Assume that they have the same mass, all the electrons have the same mass. And if you use the atomic unit, which means you set mass to be little m to be 1, h bar to be 1, the charge to be 1. And you define this dimensionless quantity epsilon, which is really the ratio of electrons over the mass of electrons over the mass of nuclei. Take square root. So typically, this epsilon is in the range of 10 to the minus 2, 10 to the minus 3, so you can consider as a small parameter. Okay. And here, the nuclei usually is heavy and move slowly compared to electrons. Okay. So therefore, if you do this non-dimensionalization of the unbounded Schrödinger equation, you come up with the following dimensionless equation, where now you see this epsilon, that's this epsilon. So this epsilon is not a rescaled Planck constant, it's this epsilon. The ratio of nuclei, electron over the relative mass ratio of electrons over nuclei. So you see this epsilon appears here, which is exactly where you usually see h bar, where h bar appears in quantum mechanics, in semi-classical scaling. Okay. And then you have this electronic Hamiltonian. From here, you kind of see that the connection with semi-classical limit. And what Oppenheimer does is that here is this equation lives in R capital M plus little m. So this Oppenheimer approximation basically want to split this capital M from the little m. Okay, they want to solve these two problems kind of separately, so that you only have to deal with R capital N and R little n instead of capital M plus little n. So the idea is following. First, you solve an electronic eigenvalue problem. So here He is the Hamiltonian that has to do with the electrons. Okay. So you solve this following eigenvalue problem. Let's assume that given the potential, you can find this phi k, which are the eigenfunctions corresponding to this eigenvalue problem, where E is referred to so-called electronic energy surface, the eigenvalue of this problem. So assume that they are, you can find the set of eigenvalues, eigenfunctions. Let's assume that these eigenfunctions are well separated. That's what this adiabatic basis means. Okay, so assume this is well separated, and these eigenfunctions we normalize it. We assume that it's a also normal basis. So that's the definition of unit product. The unit product is a canonical delta function. Once you have this eigenvalue, the eigendecomposition of HE, then you can write this original wave function. You do this decomposition of this phi. So these are exactly the eigenfunctions, where these are just coefficients. Okay. Then plug this into the Schrödinger equation, and you multiply from the left by the function. They use this also normal property. Then you can kind of write a set of equations. Now it's a system of equation for this coefficient, okay, which has this form. So this is a diagonal part of this decomposition. So you have this nucleonic kinetic energy plus this diagonal part of these potential terms. Then, of course, things are not completely diagonalized, so you have these mixing terms, which are given here, where this coefficient, some complicated coefficient over here. So this coefficient here, these are the mixing terms which characterize so-called non-adiabatic couplings. So these are really the couplings between different energy states. Okay, so here we have a separation of energy, basically kind of a diagonalized version. So each, for the corresponding case eigenvalue, you have a Schrödinger equation, which are kind of decoupled, but these are the coupling terms. And the coupling terms, of course, is, has all the interesting information about quantum mechanics. Okay, without that, it's almost semi-classical. So the coupling terms contain information, for example, about non-adiabatic crossings, interference, and Barry connections, Barry phases, and so on. So that those are very important quantum mechanical information if you want to point a chemical reaction. Okay. Well, basically, the Born-Oppenheimer approximation assumes that kind of ignore these interaction terms. So assume that things are adiabatic, which means all these eigenvalues are well separated. Okay, they don't interact. Under this assumption, then basically they just drop. So assume that this quantum information, that crossing terms are kind of weak. Okay, so we throw it away, then you already have this diagonalized form corresponding to each of these energy state, chi k. So this, of course, is completely diagonalized Schrödinger system. Each of them satisfy its own Schrödinger equation. So for each energy band, you solve a Schrödinger equation. Okay. And each of these energy bands correspond to this Hamiltonian. And here is the kinetic energy. This is the potential energy, which is corresponding to this eigenvalue, electronic eigenvalue. The K is the electronic eigenvalue. Okay. Well, there has been a lot of mathematical justification of this approximation. And for example, these are some names of people who have worked on this. However, we know that if things are completely diagonalized, then a lot of information are mixed. For example, if this is a few examples of how this potential energy surface look like. So sometimes this is, for example, one of the E1 and this E2, and this energy surface is not completely separated. Okay, I mean they might interact at one point. So this example is so-called a conical crossing, and they may not completely meet each other. But still, with certain probability, these particles can actually hop or jump from one energy level to another energy level. And this is a case which is referred to awarded crossing. Okay. So it turns out, in these cases, actually the particles do not stay in the same energy surface all the time. With certain probability, it can jump from one energy surface to the other. And actually, Landau-Zehner formula has been derived to exactly determine this transition probability. Okay, so-called a diabatic transition between two energy states using this so-called Landau-Zehner formula. All right, so that's basically the physical picture of this quantum hopping. And based on this picture, since 70s, the chemists have developed an algorithm to simulate this kind of a quantum transition using basically particles. So that's called a surface hopping algorithm. Okay. This was first developed by someone, his name is Tully. He's a chemist in Yale University, and Miller is in Berkeley. And recently it has also generated the interest in the math community, Lassa, Teufel, Schutter, and so on, or German. Well, I think Lassa is probably not here yet, but I hope she will come. So the idea of surface hopping is the following. So basically, you really want, well, we know that solving quantum mechanics is very expensive, while solving classical mechanics is much cheaper, okay, relatively speaking. So the idea of surface hopping is really, you want your most computation to be classical. So the idea is that you're following, along each energy surface, you can solve classical mechanics, okay? Then in certain regions where this energy surface get close enough, either a conical crossing or a word crossing, you do this quantum hopping. So the idea is you really want to follow classical trajectory for each potential energy surface, and then you do quantum hopping in certain regions so that you do have this quantum transition from one energy level to the other. Okay. And this probability can, of course, usually for special cases, it can be determined by the so-called Landau-Zener probability. But if this formula is not available, you need some other quantum mechanics way to determine this probability. So the surface hopping basically is a particle method. So you follow Hamiltonian for particles, except at this hopping zone, where you have to use some kind of Monte Carlo procedure, because here the probability, with certain probability, will hop. So with this probability, you can determine by some Monte Carlo method to determine with certain probability let your particle move to another energy level. Okay. Otherwise, stay on the same energy level. So it's really kind of Monte Carlo method. Of course, we know for Monte Carlo method you need a lot of samplings, because at each time the particle can only stay on one energy level. So you need to sample many samples for the law of large numbers to work. So you have to sample a lot, and because it's Monte Carlo, so it has statistical noise, and it's very efficient when the hopping probability is very low. So we see that in the word hopping near the position where the energy are very closest, the hopping probability is large. But away from it, there's still probability that the particle can hop, but the probability can be low. And if you use Monte Carlo, usually the efficiency is very low, because you have to have many samples for this to happen because of the low probability. Of course, you can avoid this Monte Carlo procedure. That's what these people have been doing, is that you split the particles. So if I have a particle that needs to hop, I kind of break one particle into two, assign the density ratio, which is determined by the probability. Say if the probability is 1/2, split the particle of mass 1 into two particles of mass 1/2 each. And then each of them follow their own Hamiltonian trajectory. Okay. But of course, because the hopping happens very frequently, eventually your number of particles will increase exponentially. Every time it hops, you have to add another particle. Eventually, you have too many particles. Okay. So these are kind of disadvantage of a so-called Lagrangian method. Okay. Another problem with the Lagrangian method is this particle can move away from each other. So eventually, in some domain, you have a lot of particles. The other domain do not have many particles. So you kind of lose accuracy. So that's the current state of art of a surface hopping method. So our interest is to develop an Eulerian surface hopping method. So the one I just presented is Lagrangian. As I mentioned, the Lagrangians the advantage of Lagrangian is very simple. You solve a Hamiltonian system, which is just ODE. Okay, very simple. And very efficient in very high dimension. And however, the disadvantage is that particle may diverge. Particles are like rays, they may move away from each other. Then you need to throw in more particles. And then you need to reinterpolate, because these new particles, you have to determine the value of density or whatever by interpolation. So it's complicated. Otherwise, you lose accuracy and you have to remesh. Okay. But the Eulerian method typically is based on solving PDEs on a fixed mesh. So therefore, it can guarantee a high order accuracy for all time, because you solve PDE on a fixed mesh. Okay. And however, the computational cost tends to be higher than the particle method, because the PDE, so dimension is higher. So you have to use some other method to reduce computational cost. For example, because these PDEs tend to be kinetic kind of equation defining phase space. So for example, you can use moment closure a tool that frequently used in kinetic theory or some local level set method and so on. So these are the methods that can be combined with the Eulerian method to reduce computational cost. So here example, I used the example of ray tracing. That's a very popular method for geometric optics to see what can go wrong with this kind of particle method. So you have a ray. At the beginning, it can be it's probably uniform distributed, but eventually you see here you have a lot of rays near caustics, but there you do not have many rays. So if you want to determine the physical quantities here, then the accuracy is very bad. You have to interpolate. You have to add more rays here such that you have enough accuracy in this region. Okay, so that's a disadvantage of a Lagrangian method. Okay, so now let me come back to the surface hopping. I use a simplest example. As I said, if you, on the electronic any-surface, we have this decoupled system of a Schrödinger equation. So here I use the example of a 2x2 Schrödinger equation. Okay, so I consider just two energy states, say one ground state, one first excited state. So this psi now is a 2x2 system, and this V, of course, is 2x2 matrix. Okay, so it's a coupled 2x2 system of Schrödinger equation. And the V now has this form. I kind of pull out the trace of V, and the rest, of course, has trace 0. And if you look at the eigenvalue of this, it's a symmetric matrix. Okay, so it has two eigenvalues, two real eigenvalues. This is the eigenvalues. And this eigenvalue, of course, most of the time they are separated. Okay, but they can be equal to each other when this guy, both V1 and V2 equal 0. Okay. So, these eigenvalues, when they are equal to each other, that's exactly so-called crossing point. That's when this electronic hopping occurs. Okay. But it occurs, of course, in low codimension. All right. Actually, this different energy level crossing can be very complicated. I mean, Hackdown, he's a professor in in Virginia Tech. In the 80s, he wrote a 100-page AMS memoir to classify all possible way of these energy levels can crossing. I mean, he basically find that 7 ways, different ways can then this energy potential energy surface can cross. It can be codimension 2, codimension 3, and codimension 5. It's a very complicated business. All right. So now I want to present. The tool I'm going to use is semi-classical limit. To do that, we have to use the Wigner transform. So here's the Wigner transform for this psi, which is a vector now. So this is a tensor product of this vector, psi times psi complex conjugate. I mean, tensor product. You take a Fourier transform of this, which give you the Wigner transform. And well, as I said, this is a 2x2 system, so there are 2 Hamiltonians associated with this system. That's given by this. Okay, this 2 Hamiltonian system, and we have to introduce a projection operator, so we can eventually we are going to project this 2x2 system into these 2 eigenspace. So that's the projection operator. So this chi is really the eigenvectors corresponding to these eigenvalues. Okay. All right, as we know, the semi-class limit, the Wigner transform is really a powerful tool to study semi-class limit. So the idea is that given this system of Schrödinger equation, if you use this Wigner transform, then you write a equation W, which is a matrix, 2x2 matrix, and you satisfy the so-called Wigner equation. Then you pass the limit. You set it equal to 0. You try and find the limit, and the limit I call U. And if you take the trace U tau to be the trace of U, project into tau's eigenspace. We have tau equals 1 or 2 eigenspace. I call this U tau. Then it turns out this so-called semi-class limit when epsilon go to 0 is this Liouville equation. Okay. So here we have 2 independent Liouville equations. One corresponds to each eigenspace. So this, of course, the semi-class limit was studied by some of people who are in the audience: Peter Markovich, Gerard Mauser, Pupot, and Thierry Paul, who is here, and Pierre Lyons. So that's a well-studied semi-class limit. Okay, assume that its eigenvalues are separated. Then you get this. However, what's interesting here is that these eigenvalues, at some point, the eigenvalues are not separated. Then, of course, the semi-class limit breaks down at those points. And so to characterize what happens, so basically what happens that away from this surface, the hopping area, you can use this Liouville equation as the semi-classical limit. But you need something else at the hopping region to describe this quantum transition, okay? Because these two things, they just follow their own Hamiltonian trajectory. They never interact with each other. They interact at the hopping region. They're going to interact through this so-called Landau-Zener probability. So here example how you calculate this probability. I give a very simple example, simple ODE. Okay. So here you have a symmetric ODE here, and it has two eigenvalues, plus or minus t squared plus tau squares. So the Landau-Zener basically studied this ODE. They asked the following question. So assume that, well, this is the eigendecomposition for this matrix. So assume that if you start with, for example, you have a pure state initial state. I mean, start at t equals minus infinity. Assume that you only have particles in one of the eigenstate. Okay, so the density of particles, one of them is 1, the other one is 0. So you have a pure state. Then what happens at t equals infinity? Through the dynamics given by this ODE. What happens at t equals infinity? So basically they solve this problem. Then this is the transition as a result of solution of this equation, which says that at t equals infinity, the dense distribution of this plus or minus corresponding to two eigenspace exactly is the initial states, which are t equals minus infinity, times this matrix, which is really this, that's the scattering matrix, which tells with how much of this mass from the initial state goes to the other states at the end. Okay, and this t is equal to this. It depends on this delta, and some epsilon, this epsilon tilde is given by this. So it's that's exactly so-called Landau-Zener probability. Okay, and so of course when delta goes to 0, this is 1, which means that it does not hop. If delta goes to 0, this is a complete diagonal system, so they don't interact with each other. They follow their own trajectory. But if delta is not 0, you see with certain probability, some of this mass of one particle will be distributed to the other particle. Okay. All right. So how do we utilize this Landau-Zener property in our this Liouville-based approach, semi-class limit? So the idea is, well, first you have to determine where you have to use this probability. It turns out this hopping occurs near so-called minimal energy gap. That's when these two energies are very close to each other. So that's where you have to use this probability. Okay. Away from it, you still hop, but the probability is very low. I mean, probably you can ignore it. So so that's where this two energy surface reach the gap of any surface reaches the minimum. Is given by this S star, and at S star you have to use this transition probability, which is given by this. Okay. For the system, for this 2x2 system, and our study. So that's the formula for the transition probability. And what justification of this Landau-Zener formula is also of reason mathematical interest. For example, Gerard and Lassa, Teufel, and so on. So they have been trying to justify this Landau-Zener probability in the semi-class limit setting rigorously mathematically. All right, so this is our Eulerian surface hopping. So our approach actually is very similar to our previous work, where in the past five or so years, I've been using semi-class limit to study quantum barrier, quantum tunneling. And this phenomenon is very similar to quantum tunneling, where the quantum tunneling basically tunnels through barriers, but on same energy surface. But here the particle also tunnel, but tunnel to different energy surface. So the phenomenon is very similar, okay, different type of quantum tunneling. So the idea, when we do the quantum barrier, the idea is we will still use Liouville equation, which is classical, away from the barrier. But to go through the barrier, we have to use the interface condition, which build in this quantum scattering. So the interface condition tells you how much the particle should be transmitted, how much should be reflected. Okay. So here is very similar, and so that's previous work for quantum and classical barriers, semi-class limit through barriers. So we have when you introduce this numerical method. So the idea is the cost method is classical, but it allows quantum tunneling, okay, because of this interface condition. So this is our approach for surface hopping. So again, along the two energy surface, we solve the Liouville equation by whatever method that you like. Okay, it's classical. And then at the point where we need to hop, we use this Landau-Zener transition. This is exactly the scattering, the transition in the matrix determined by Landau-Zener. So basically the flux, this is the flux corresponding to, these are two flux corresponding to the two Liouville equation. So the flux in the normal direction toward this hopping surface should undergo this transition. So this is the minus are really the pre-hopping stage, while the plus are post-hopping stage in the normal direction. So you multiply by either the 1 minus t or t. So with probability t is going to with probability is going to go to the if you start with ground state with probability t, you go to the first excited state. With probability 1 minus t, you stay on the same state. That's what this scattering matrix tells you about. Okay. All right. Of course, you have to choose the crossing region, which is about square root of all the epsilon away from the smallest energy gap. So you have to do this in the small neighborhood of the minimal energy gap. Because away from this, of course, the hopping probability is so small that you can basically ignore it. And it turns out, of course, this innovative condition you can use it everywhere. It does not have to use only in the hopping region, because this is really just like a boundary condition, interface condition. You can apply that everywhere once you know the probability. Of course, if it's too far away from the hopping region, the probability is so slow, basically t is 0. Numerically, it's within your numerical tolerance. Okay. All right, the next is that how do we do this numerically? So we have this PDE, the Liouville equation, you have this hopping condition, how to build that into the numerical scheme. The idea is actually, as we have done before for quantum tunneling, is really you can build in this condition, the interface or hopping condition, into your numerical scheme. So your numerical scheme will do the hopping automatically. Okay. There's no emotion involved. The code will do it for you. So the idea is actually very simple. This is the finite volume discretization of this Liouville equation. So this is du dt, this is du dx times psi. Okay, du dx, du dy. This is a two-dimensional problem. This is du d psi, du d eta. So that's the forcing term in the Liouville equation. So this is the derivative of the potential. Okay. Now the key idea is, notice usually if we discretize this Liouville equation by finite difference, this is just the numerical flux. But now I have this minus plus. So that means in the hopping point or the interface point, my flux will be discontinuous. The reason is because when you hop or when you're tunneling, and this flux are going to, it's not continuous. Okay, it's not like a typical way of solving transport equation. Here we solve a transport equation by building this condition into the flux. So the flux, we're going to use a kind of an upwind scheme by using this. This basically, if t equals 0, then it's basically upwind, because whatever comes in, it goes through the interface. Your flux, numeric flux, pick up whatever comes from upwind direction, right? That's upwind scheme. But now we are doing upwind scheme in a way that is consistent to this condition, which basically is the following. Okay. So this is a typical way to do upwind. Usually what is second order upwind, if particle is moving with a positive speed, your flux, you pick up your flux from the cell from the left. So that's upwind. Well, this is just second order correction. You forget about you don't have to worry about this term. Okay. But now usually do this, but if you have a hopping, then of course it's not ui plus 1/2 equals ui. Instead you have to multiply the right one should be the left limit multiplied by this transition probability. Okay. Because not the whole thing will cross the interface. The t portion of it will stay in the original surface. The 1 minus t portion will cross the interface. So that's why you have to multiply by this. Okay. So you have to do this for basically at every interface point. Okay. Similarly in the psi direction. And for example here, I mean, these are the probability that goes to a different energy level. These are the positions that stay in the original level. You multiply by t. So it's kind of a generalized upwind scheme. Okay, but so by doing this, and then this scheme, the flux already contains this hopping information. If the t is 0 is reduced or original upwind scheme for the Liouville equation, for linear transport equation. But if t is non-zero, this flux gives you the right hopping. And you can prove some simple theorems which under the right CFL condition. Okay. And the U, remember the U is energy density, so it should remain positive. You do have positivity, and you have this L1 stability. Okay. So you have these properties, this method. All right, now I show you some examples. So this is so-called linear isotropic potential, where you have this symmetric matrix, where the eigenvalues actually, if both x and y equal 0, you have two eigenvalues which both 0. So that corresponding to exactly this conical crossing example. Okay, they touch exactly in the origin when x and y are both 0. So that's a solution of the Schrödinger equation. So if you start with the ground state, okay, then at some later time, part of this goes to the first excited state, and after some time there's another hopping. So more of this will go to there. So this is density distribution. You start with the pure state with so the first energy state has probability density 1, the other one has 0. After first hopping at this point, then the density of course lower to this because the other part goes to the first excited state, and this is second hopping. So here the blue line is the quantum simulation. We solved the original Schrödinger equation, and these dots are exactly this classical plus this hopping interface condition that give you this red dash. So you can see a very nice agreement. Yeah, sure. It's a conservative scheme. Yeah. The total mass is conserved, but each year is not because it hops to the other. Yeah. The total mass. Well, you have this. Well, actually, it's okay. It's not exactly. It's a stable. It's a L1 stable. Yeah. The total energy, the flux is conserved. I mean, the flux is continuous across the interface. That's why you get this condition. Numeric total mass is conserved. Yeah. All right. So this is another potential where chemists use a lot of Young-Taylor potential, which looks like this. So you have two energy surfaces which is kind of toward the same side, but they tangent at one point. Okay, so that's the matrix. That's the potential matrix. And again, this agreement, there are 3 hopping stages. And you always see a nice agreement between the full quantum simulation and this semi-classical approach. That's a good question. I forgot. It's probably 1/1000. Between I forgot. It's 10 to the minus or 10 to the minus. I don't remember exactly. Yes. Well, it's in the paper, but I forgot to put it here.
So the hopping happens only in one direction?
It can go in different. Well, it can go in different directions. I mean, this method does not require that it goes one direction. Oh, in this case, yes, because that's right. Well, here you have once you hop to another one, you just move away from the hopping region. That's what happens. It does not come back. It depends on the potential. You can find a potential where this can come back and interact. That actually happens. Physically, that happens. But for this example, they just once it hops, it does not come back to the ground state. Well, it has to do with how, I mean, the potential, the form of the potential. Well, okay, so these are, of course, the preliminary results where the basic advantage of the Eulerian method is that there's no Monte Carlo procedure, okay, or exponential increase particle. The number of Liouville equation you solve is fixed. It depends on how many energy state you want to keep, no matter how many. I mean, here I give example of 2x2 system, but same idea works for any n/n system, of course. And it's fixed, and I is always fixed. And you offer high order accuracy, no matter you can use high order method. And you can use for any number of energy state, right? Because I mean that really only change the number of Liouville equations. But I mean the setup, mathematical setup is completely the same. And as I mentioned, the flux, the hopping condition can be applied everywhere. Okay, whenever the transition property is not negligible. Okay, so this kind of avoid the low free efficient Monte Carlo method, because for Monte Carlo method, if the probability is low, most of the time the samples have to be abandoned because it does not happen most of the time. So the efficiency is very low, but this method does not have that problem. Okay. Actually, the efficiency does not depend on where you how many point position you have, because everything is in this numerical flux. The cost of flux is basically the same. Okay, the only thing different is this value of t, which can be 0 when you do not hop. But the computation costs the same, whether it hops or not. Computation cost is basically the same. All right. So, well, there are several ongoing projects because this, as I said, it's really preliminary results, and there are many other things. For example, these examples are both conical crossing. When you have a water crossing, when this energy surface do not really touch, then the same formula can work, except where the particle momentum will change, because total Hamiltonian is conserved. But when this energy do not touch and you hop, the momentum will have either accelerate or decelerate. So you have to build in that into your method. Another important phenomenon is interference. As I was asked, this hopping, the particle can move away from hopping zone, but may come back. For example, if you have a harmonic oscillator, then this particle do come back. When two particles at different energy level reach the same point and hop, there's a quantum interference. And this method, of course, does not pick up any kind of interference because it's based on Liouville equation. As we know, the Liouville equation does not contain any phase information, so you do not deal with this interference. And also mixed state. Another thing that is Landau-Zeno, well, so far we have been using this Landau-Zeno formula, but that you can only derive this formula for very special potential energy surface. But for most of the application, of course, its probability cannot be found analytically, and you have to compute it some numerical way. Okay. Another way to overcome this problem of phase information, loss of phase information, is that instead of using Liouville equation, which is really geometric optics, you can use, for example, Gaussian beam. And Gaussian beam is the method that can preserve the right caustics and also the phase information. And actually, we have a recent work where with Hao Wu and Xu Yang, where we actually formulated Gaussian beam very similar to geometric properties, again by Liouville equation, except it's the Liouville equation in complex plane. So that allows us to capture the phase information. So our idea is to use Gaussian beam for the interference instead of just a classical Liouville equation. Okay. Well, yeah, actually, Gaussian beam was also used in the chemistry community by Heller, where they call it Gaussian wave packet method. They are really the same thing. Another related problem is if you have a quantum mechanics in a periodic lattice, there you have used block decomposition. And its block eigenvalues also have the same problem of mixing. And so far, all this symmetrical limit for periodic domain has been relying on the separation of the Bloch band. Okay. But sometimes Bloch band cannot be separated, and they are mass transfer from one energy band to the other. And that phenomenon is very similar to surface hopping, so I certainly expect whatever we did for this surface hopping can also be used for block decomposition based on a numerical method. Okay. All right, so that's all. Well, thank you for your attention.
Well, thank you, Shi. Questions, comments, remarks?
So on the curve, coming back to the curve which showed the transition, what determines the scale of with the transition region? So when you have
so these are conical crossing. These are conical crossing. So so it's either like this. The second example was like this. I mean, the kind of tangent is two energy surfaces. So basically, well, this is a hopping point. You cannot just use this for one point, okay, because it's a singular. So basically, choose a domain which is all the square epsilon region around this hopping point. Then you apply this formula. Okay. So it's a few mesh points. All the square epsilon neighborhood of this hopping point. That's where we use this formula. Use this interface condition. Yeah, serious?
It's a very naive question, but Bono-Beinheimer is an approximation, right?
Yes.
So what's the incidence of this kind of phenomena on the true evolution of the wave?
You mean the unbodied Schrödinger equation? Yeah, exactly. Well, that's the physical picture that it happens because this is really a Born-Oppenheimer approximation Okay, so up to this point, actually, there's no approximation. So up to this point, there's basically no approximation. Okay. So you basically try to diagonalize the original unbounded Schrödinger equation using this electronic eigenvalue, eigendecomposition. So you have this equation. So this actually contains all the important quantum mechanics. Of course, Oppenheimer basically does is assume these eigenvalues are well separated and they drop this term. Then you can use semicolon approximation for this nuclei for each. Okay. So what that basically tells you all the quantum transition, Barry phases, all these interesting quantum phenomena are contained in this information. So what we did is first we threw this away, then basically approximate this by semicolon limit. Then we try to recover some information that's here. You cannot recover everything because that would be a full quantum simulation. But the first step we want to recover is from here. We recover London-Zeno transition. The next step we want to recover certain phase information, for example, Barry phase, which is very important things in this electronics. So those are all contained here. We try to take a few information here. You cannot capture everything here because that would be complete quantum. So you have to know what you want to capture. Then you see, okay, based on the same cluster approximation, can you add a little bit more such that you capture certain quantum information? That's what we have been doing. So first step is to capture this London-Zeno transition. The next thing we are doing is try to capture Barry phase. To do that, you need some phase information. So we're going to use Gaussian beam, for example.
You mean at this point?
And this one is there's no approximation, right?
But if you want to use Gaussian beam, you need to use this equation.
Well, I still use that, and because that's good approximation of semicolon approximation. But Gaussian beam is not enough. You still have to use something from here. London-Zeno thing, kind of things you want to. Or another way we're doing is some kind of a multi-scale approach. Within the hopping zone, we solve Schrödinger equation, but only in the small neighborhood. Away from it, we use Gaussian beam. So we are playing all these different ideas.
Let me just add that in the case of band crossings, there is very few analytical results so far.
Yeah.
There's just, if I'm not mistaken, there's just a paper by Patrick Gérard with co-workers. Maybe there's also some Fermanier. And we really don't have we are far away from a complete theory of understanding how much mass transfers from one band to the other and so on. It's really a tough problem. Any more comments, remarks? Well, if not, then let's thank Shi.